Okay, so it's my pleasure to introduce Jorge Pereira for the last talk of the day and talk about codimensional foliations in positive characteristics.
Okay, thank you very much. Thank you very much for the invitation and for the opportunity to share some mathematics with you. I will start commenting on a result that Callum alluded to this morning. So it's a theorem by Joannoulou. So in the field by Joannoulou's theorem, he has another very influential theorem also, but this one is about the very generic foliation on P2. So let F be a very generic foliation on P2. I will explain in a bit what I mean by very generic. For this result, it is a result about foliations over the complex numbers. We have very generic foliation, P2, with ample cotangent bundle, the dual of the tangent bundle mentioned this morning. So I will write this guy as OP2 B minus 1, just because of bad habits of the field, with D at least 2. So this D is what we call the degree of the foliation. It has a geometric meaning, is the number of tangencies with a general line. Exercise. So the conclusion is that then every leaf of F is a risky dense. Okay, so what do I mean by very generic? So it seems natural to parameterize the foliations on P2 having this cotangent bundle by an open subset of the projectivization of the P2 tensor D minus 1. Because a foliation like that comes with a map, TF to TP2, and you can just produce a section from that. And I see this section, or at least this section up to a multiplicative constant as a point in this projected space. You might want to get rid of the foliations that has, or the sections that has codimension 1 singularities. So that's why I say that we have here as a risky open. Let's call Fol D. The space of foliations on P2 of degree D. It's as a risky open, where essentially you put this singular set of codimension 2 conditions. And very generic, I just mean, or Joannoulou meant, is just the complement of a countable union of proper in the sense that they are not the whole space, Zariski closed subsets. Okay, so this is a result from the 70s that Joannoulou wrote in his lecture notes, famous lecture notes. And the proof by Joannoulou, it's a standard. With a statement like that, you might imagine how the proof goes. You must have 2 steps. One is to show that there are a countable union of proper Zariski closed subsets of foliations have a algebraic leaf, a leaf which is not Zariski dense. And the second step, you have just to produce an example. It's the standard argument that you see in a lot of results on moduli or behavior of generic curve with the generic line bundle and things like that. And so the first step is the standard. It shows that every for L and the set of foliations having invariant curve of degree at most L, or here perhaps we don't even put curve, you could put divisor, because we should allow multiplicities to have this set to be closed. We should allow multiplicities, multiple components, several components, and so on. But this is essentially standard. If you want, exercise 2. And the second step consists in producing an example. And that's the hard part of the proof. And João Lulu himself gave an explicit example. The set is closed. Thank you. Is Zariski closed? Is Zariski closed? At this point, you just prove that it's Zariski closed. You don't know if it's everything or not. And in the second step, you have to produce. He produced an example. A foliation have no invariant algebraic curve. So will be a point outside all these Zariski closed subsets, and then you would have that in the complement, this property also holds. And he gave an explicit example. This example, it's defined on projective coordinates by a vector field. It's the foliation defined on C3. By yd ddx plus zd ddy plus xd dz. So this if d is at least 2, these examples has no algebraic invariant curves, and it's very nice. So a long time ago, while I was looking for a PhD thesis problem, I came up with the idea, okay, it's hard to find a PhD problem, so a PhD thesis problem, so let's try to prove things that we already know that's true, that's safer, right? So let's try to do another proof of João Lulu's theorem, and for me. And I want to do that, and so I had this idea that, well, if the game is only to produce one example, okay, or at least show that this example has no invariant curve, why not try to argue with the reduction mod P of that example or any other example? So this is an example defined by a vector field on C3, but it's defined over Z. In principle, we could reduce it modulo any characteristic, any prime, and see what happens. Okay. And the first thing that I did was to put on a computer. Because why positive characteristic? What is different, right? What happens in positive characteristics? What extra feature we have in positive characteristic? The point is that we have new operations. For if you have a vector field, V, you can canonically produce another vector field. So you can, if the characteristic is P, we can produce another vector field just by iterating this vector field. So what do I mean by the iteration of a vector field? Think of the vector field as an operator, as a derivation, and I can just iterate, apply the derivation to functions p times, and or in general, you are going to have some higher order differential operator, but in positive characteristics, something very interesting happens, right? Because when you take Vp and apply to the product of V times G, Leibniz rule will imply that this thing will be something like V equals 0 to P, VIF, Vp minus Ig, but here you have to put some combinatorial number. I think it's IPP. And if the characteristics is P, then the only two terms survive is the first, V0F, which is of course F, and Vp 0G, which FVPG plus VPF. And so you have this nice feature that starting with a vector field, you produce another one. And on the top of that, if I have an invariant curve, so this means that, as I explained this morning, the V of F will still be in the ideal of C. So this means that at least locally, I will be able to write something like that. And then if you iterate, you are going to get something here times F again, just by seeing what happens step by step. So if I had this curve that is invariant, so I still have another curve, which is it's also invariant algebraic curve, invariant by V. So C is also invariant by Vp. Very good. So now you have a strategy to prove that something in characteristic 0 does not have an invariant algebraic curve. Start with a vector field, let's say defined over Z. Assume that it has a complex invariant curve. Specialize to have it defined over a number field. Apply Galois in order to produce another curve, which is perhaps not irreducible, but defined over Z, reduce mod P, and verify that the curve that appears in the tangency locus of V and Vp is not invariant by the reduction mod P of V. And in principle, in a small characteristic, you can do all these computations automatically. So I tried to do that and didn't succeed. Every time that I put an example, well, Jean Lou examples and others, it always appears to be invariant. But then it turns out that this guy is invariant. The point is that what I learned is the following proposition or theorem. That if I have, let's say, a V vector field on H2K, K positive characteristic, this is different from 0. Let's assume that the divergence, if the divergence of V is different from 0, then the 0 locus, the irreducible components of the 0 locus of V equals 0 with multiplicity prime to P are V invariant. Indeed, in this formulation, don't even need this assumption. Sorry.
Exactly.
Sorry.
What is written in the brackets exactly?
V wedge VP. I don't even need this. In this formulation, I don't need the assumption. We assume two things, yeah. If it's identically zero is invariant by definition. The zero ideal is invariant by the derivation. But yeah, all right. I have to assume that is different from zero. And that assumption that I put here was something to guarantee that this guy does not have all the components with multiplicity P. Here by components, I mean, I just take the composition in irreducible factors and I look into the powers, the multiplicity are just the powers which they appear. Right? And the explanation for this theorem was rather simple. As Frederic mentioned, when V wedge VP is equal to zero, we say nothing. Essentially, this result says absolutely nothing. But if V wedge VP is different from zero, then what you have, if you try to think in terms of the geometry in characteristic zero, at least to have some intuition, you have here this orbits of V, which do not exist in positive characteristic, but anyway, it's just a sketch. And VP is not parallel to V, but of course, essentially by its definition, it commutes with VP. In characteristic zero, this means essentially the following. If I take VP, or rather, if I look to the flow of the vector field generated by VP, this condition means that it leaves orbits of V into orbits of V. So essentially, perhaps a better picture would be like that. The length of the vector field VP is proportional to the distance between the leaves. So when I take the flow, when it commutes, I will end up in the other page. Of course, this makes no sense at all in positive characteristic, but all this chatty can be translated into equations involving the Lie derivative and everything that you formulate in a completely algebraic way, and you verify that this will hold. So when this happens, what happens is that the tangency and the tangency of VP and V must take leaf into leaf, but since it's tangent, must be completely tangent to the leaf. So this is essentially what shows that VP is an infinitesimal symmetry. Of the foliation defined by V. And this implies that V wedge VP is invariant. Of course, you have to translate this into algebra, and then you're going to see this condition of multiplicity prime to P appearing. It's nothing, it's not deep, it's not very hard, but I don't see it, don't think it will be very instructive to do the computation here. But you can look in the paper.
By F, you mean the span by V?
F defined by V.
Yeah, so you mean the span subbounded by V.
Exactly, yeah.
Yeah.
Very good. And there is a version of this result also for, so this is, I was stating everything in K, but then there was this result of Cerveau, Lins Neto, Lorey, myself, and Touze, that we prove, I think in 2003 or 2004. Which says the following. So let F, codimension 1, foliation, on X, a projective manifold X on X, a projective manifold defined over K, positive characteristic, and if V is a rational section of the tangent bundle of F, codimension 1, rational section of TF, and such that VP is not, or such that VP is generically transverse to TF, then the quotient of omega by omega VP is equal to 0, where here omega is a one form with coefficients in the normal bundle of F. So just the same way that if I have a foliation of dimension 1, I have a vector field with coefficients in the dual of the tangent spanning or defining the foliation. For codimension 1 foliation, I have this one form. And here, of course, it's just the quotient. So these are two. This is a section of omega 1 X tensor and F. I do the contraction with a vector field. It becomes a section, a rational section of NF. And I take the quotient and I get this is a rational one form, right? So it makes sense to take the derivative of a rational one form. And I claim that this derivative is 0. Very good. And so this, we did this a long time ago. And for a while, it was just a curiosity. Because you see, already here, if you compute degrees, V, let's say, think of V as something of coefficients of degree D, then V to the power P is something with coefficients of the degree P times D. Very large, which doesn't bug me, but what really bugs me is that depends on P. It gets larger and larger when P grows, and seems very hard to lift any of this information. For instance, it would be very nice to lift these invariant algebraic curves to characteristic 0, but they do not form a bound family, so you cannot lift. So, so more or less 10 years after this result, in a paper with Frank Loret and Frédéric Touzé, we saw that if the foliation has some assumption, then you have some hope to lift this information. So when the canonical F of F is trivial, is numerically trivial, then and plus F or TF semi-stable, we could show that Loret, Touzé, we could show that this form we could bound the poles of not saying that for any V that we produce, we'll have something of bounded poles, but we could, after cleaning up P powers, we could produce something with with low degree. And this allows us to lift the information to characteristic 0. The part of the pose. Characteristic 0. And this gives information, useful information you can use and build with other ideas to end up describing these foliations in Codimension 1. Okay. Very good. So these all, but still, you still have this feeling that it has rather limited use. You don't expect the general foliations far from looking like this. The general foliation will have ample or big or canonical bundle, and at least will be very far from trivial. And all this just seems to be some bunch of crazy divisors that vary with P that we have no use for. But the point is that if we look a little bit more careful in the construction, there is something that indeed varies nicely with P. So let me try to describe a little bit better the situation with a little bit more care. So the things that I want is to look at this map, right? The whole discussion started taking a vector field and looking for its P power. So let's consider Tx as a sheaf of sets. Forget any structure that Tx has. It's only a sheaf. It's not a Abelian group, it's anything, it's not anything. So we have an operation that takes a vector V and maps to Vp. And as I said, this guy is nothing. It's not additive because you can try to compute this thing. It's not additive. Because when you compute this thing, you get something like V1 to the power P plus V2 to the power P plus Lie polynomial in V1 and V2. If you want to amuse yourself, you can open the book of Lie algebras of Jacobson. You are going to have explicit expressions for this Lie polynomial for P equal 2, P equal 3, P equal 5. And then he doesn't have space in a single page to write down the expressions. They get really big, really messy. But the good thing is that they are Lie polynomials, meaning that they are iteration of brackets of V1 and V2. It's not, well, if it's not additive, there is little hope of saying that's so linear, right? So, but this already gives a hint how to fix the situation, right? So the first thing that we get is that, well, it's, we are going to have a Lie polynomial, and we are essentially interested in foliation. So if I look at the foliation instead of the whole tangent bundle, and here we mod out by TF, you see that this guy suddenly becomes additive. Just because this is a Lie polynomial, and if both guys are in the tangent sheaf, the Lie bracket still is in the tangent sheaf, and we are just iterating this operation, and so you get something that lies here. So this is good. Well done. Now we are more. We can even, if you want, we can even compose this to land in the NF, right? Just taking the B dual. But you still are not completely satisfied because this thing is not OX linear. So this is a result of Jacobson. And it's not OX linear because when you do this, you get something like V V1P plus V, put a V here, VP minus 1F times V or something like that. I never remember the sign. Okay, so this is not it's not all linear, so that's unpleasant. But then we are working over algebraic closed field. I didn't say that, but let's say it now. And we can have this, we can look at the absolute Frobenius map from F to X. And if we pull back TF by the Frobenius, this is essentially, we keep the same sheaf of abelian groups, but we change the structure of O module in such a way that this guy now becomes linear. Okay, and this, so note that this lies in TF, so it goes to 0, right? Very good. So we have a map, a morphism of all modules, and we can try to do geometry with it. It's a map of all modules, more or less describing these tangencies of the divisor with of the foliation with its pth power, let's say. And this divisor that was coming up until now is just as in this morning in another slightly different situation, but will be the divisorial part of the support of the co-kernel. Because NF has codimension 1 in ours. Well, that discussion works in any codimension, right? So far this discussion works in any codimension, but let's assume that codimension is 1, meaning that NF is a line bundle. And in this situation, the image of that morphism, let's call it psi. Psi, which is that morphism over there, will be something like NF, tensor ideal sheaf. Ideal sheaf. And so I will define delta F as the divisorial part of Z, which is essentially what we were computing before doing the wedge of phi with Vp. I will assume that if, assume, of course, that the image of psi is different from Z. And you probably might be wondering how serious is this assumption of the image of psi different from 0, but when the image of psi is equal to 0 in any codimension, we say that F is P closed. And in this situation, you can form quotient space using very particular features or positive characteristic. You have a factorization of the geometric Frobenius. So this is and you have a factorization of purely inseparable. No, it's not purely inseparable. You have well, I will not say anymore. But so this is the case where the foliation is algebraically imputable. Okay. So the idea now is to do what? Well, I already said that in dimension 2, it seems to very hard to extract any information from it, right? Because in dimension 2, the only information that we have essentially from this exact sequence is the image. TF has rank 1, NF has rank 1. So I have an idea, which was essentially given by the zeros of V wedge VP, and the kernel is trivial. No information at all. But what we want to look at is the kernel of psi. This is a subsheaf of the pullback by Frobenius of TF. We'll have codimension 1 here in Frobenius of TF, and seems to be worth studying. The first issue is that it's not completely clear if this guy will give rise to a subsheaf of TF, right? It's completely unclear in principle, if this guy is Frob star of a certain E for some E contained in TF. There is no reason for to have this property, but it turns out that in this case, or if I have the following proposition, if F has codimension 1 and image of psi different from 0, then there exists VF, a distribution on X such that the tangent sheaf of VF pulled back by the Frobenius is the kernel of psi. So what is that? So a distribution is essentially the same thing as a foliation in the definition that Carl gave this morning, with the only difference that we do not impose any involutiveness. It doesn't have to be closed under the B bracket. It's just a subsheaf of the tangent sheaf with torsion-free co-kernel, a saturated subsheaf of the tangent sheaf. So you have this thing. And so the geometry starts to appear. So we have a canonical way under this assumption, codimension 1 and the image different from 0, to produce a subdistribution of any given foliation. It seems quite curious. We have no idea, no procedure to do that in characteristic 0. So it's funny that some geometric fixture like that appears in positive characteristic, but do not appear in characteristic 0. So this I proved with Touze 5 years ago. No, I don't know, 2014? 13, yeah. But you proved the other one, so. It's a shame that they are recording. Otherwise, I would say, I would make other comments. Very good. But so this is the thing. But again, 2 comments in general. This property does not hold for the kernel of psi. There are foliations where the kernel of psi do not have this property. There is no subdistribution, but we can prove, following an argument that Touze and Fred gave a long time ago, that if the foliation is p-dense, meaning that the smallest p-closed foliation containing it is the whole space, it's the foliation with only one leaf, is Tx, then you also have this property. And then this is this p-closed in codimension 1, p-dense in codimension 1 is essentially the same thing as having psi non-trivial. But anyway, let's not go in this direction. Let's stick to codimension 1. But you have this guy, very good. And there is one nice feature, right? Because this guy appears as the kernel of this map. And we have this. And the nice thing is that looking at the determinant of this exact sequence, you see that the degree of TF, of TVF, meaning the degree of its first Shan class with respect of any polarization, is bounded by a function that does not depend on P. It's constant when you vary P. So this guy belongs to a bounded family. So here, if we are reducing something from characteristic 0. So the key point is that this can be written just in function of the degree of NNF and it's a function of the degree of NF and the degree of TF. Has nothing to do with characteristics. So while this divisor behaves very wildly, you had this P component there, this P linear dependence on P. This guy, TVF, varies quite nicely when I vary the characteristic. But there is one bad news. I'm not keeping track of the time. Okay. Bad news. TVF is just a distribution. In general, it will not be integrable, not involutive in general, or VF. Not TF, TVF is not involutive in general. Okay. But anyway, to be completely honest, every time that I learn something new about this setting, I see more and more beautiful geometry emerging, but I don't care about foliations in characteristic P. I care about foliations in characteristic 0. I have my personal obsessions that every time that I learn something, I try to apply to them. And I would like to apply these things to foliation in characteristic 0. Take a foliation in characteristic 0, take an integral model, reduce mod P, and try to lift this information back to do something useful. And so the good news is the following. This distribution can be lifted, is involutive when the foliation comes from characteristic 0. So let's state like that. The statement will be a little bit more technical. So let F codimension 1 foliation on X over K equal K bar, characteristic of K. Assume that F lifts or can be extended to a foliation defined over the ring of length 2 with vectors of K. Then PVF is involutive. To be completely honest, this theorem is just a very simple local computation, which is indeed an amplification of an example of Miyaoka. So you have this very nice picture, right? You have the foliation, codimension one foliation. Let's assume, let's just to keep things simple, take a foliation defined over Z. You can reduce it mod P. When P varies, for each P, we have this codimension one, codimension two subfoliation, which lifts to something which will be integrable, but perhaps will be not unique, but anyhow, it lifts. We have something of this geometry, that this clear geometry that we see here survives in characteristic 0. Any question? Let's see. We only probably you can. The argument really, I just localize at the closed point, look formal power series, and do the. I don't need it to extend the whole space. I only need to.
W2, or because you put some principle for a ring which is ramified with W2. For instance, the variety which are not liftable over W2, but you can ramify this ring. And
Probably, we have to. You have to explain me that. I'm not an expert, because at the end of the day, here, the computations is local. So it's not about the lifting of X, it's lifting of F restricted to some even formal neighborhood of a closed point. So it's it could, I think that it ramifies, does not, it's, so just to say, the argument is really easy, just a computation. It really doesn't matter. As I'm saying, the strategy is to assume that not the case, and you do the computation in a closed point, in the formal completion of a closed point. So it doesn't matter. So what we do to use the computation of this thing, right? So to do the computation, we have to have a better hand on, perhaps I will try to explain how the argument here goes. So what we use to do the computation. So the key observation that is new to this work with my former student, Codimension, is that we can describe this TVF can be quite precisely described. So the observation is that this guy will be the kernel. Let's just call eta. Remember that we had this one form, omega wedge omega VP, from the statement of the theorem by the 5 authors. So this is a closed rational one form defining F. Okay. And TVF is what? What we have proved is that TVF can be recovered as the kernel of the restriction of the Cartier transform of eta to TF. Okay, so you have this operation on closed one forms in positive characteristic that we there's another of these things that we don't see in characteristic 0 that maps is a map from closed one forms to one forms. Again, the map which is not linear, but it's P minus 1 linear, and to make it all linear, you do something like that. And this is a map that will take a closed one form, you give a one form back. As essentially, it indeed is working for any I. One way to understand this map is to describe how it works on I equals 0. What is a closed 0 form? Is a function with 0 derivative. A function with 0 derivative is a pth power. And this map is just take out the pth power. So this is a way of taking the pth power, take the pth root of differential forms. So it typically, if we look at 1, we'll do something like that. We'll send dx to 0, xp minus 1 dx to dx. and will be Fe dx. Well, it will be P linear. We will go to F. Okay. So this is an operation that you can do with one form, and if you do this with that one form, we get rid of this guy. And so the proof of this thing is just, well, assume that this guy is not integrable. Well, you restrict to dimension 3 by hyperplane sections, and you look at a point where it is actually not integrable, this Cartier transform, and you apply the inverse of the Cartier transform, which is easier to describe, and you deduce that the original form was not integrable. It's just a simple computation, half page, one page computation. It's not, okay. Very good. So far we don't have many applications of these ideas, but I believe when time is right, they will come. But somehow we have some modest applications of it. So we can, let me just before, let me state one of my obsessions, and I'll try to explain why I think it's related to this thing, and how to prove some very modest results in this direction using these techniques. So the conjecture is the following. So it's a conjecture aiming at describing the geometric structure of codimension 1 foliations on a projective variety. So let X be projective. F codimension 1 foliation. Then we have two possibilities, conjecturally. The possibility A is that there exists map from X to a surface, rational map, and a foliation as surface, and a foliation G on S, such that F equal to pi star of G. And this is one possibility. And the other possibility, to make a connection with the talk of Remy this morning, is the following. There exists V rank 2 VW, V nabla, rank 2 vector bundle over X, flat, in the connections flat. So we are going to denote the age, the foliation on PV defined by the projectivization of flat sections of V. So there exists this, there exists a rational section from X to PV, such that F is equal to sigma star of H. So, some sense, foliations either come from surface, and on surface, this is very wild, dynamically speaking. No transverse regularity. And either they come from flat projectivization of flat connections on rank 2 vector bundles. And there you have a very strong, that's the case that we call transversally projective. You have very, very rigid, very structured transversal structure, transversally projective. Okay. And the point is that the first result that I stated about the existence of a rank 2, it shows that there is a very particular kind of flat connection on on a trivial extension of the normal bundle by OX, where F fits in this picture. So this is always holding characteristic P. Characteristic P, something stronger than this, always hold. The closedness of that one form implies that a stronger version of this holds. But again, the problem is that you're going to produce a flat connection, but the poles will not be bounded when you vary P. But anyway, if you believe that something like that is true, you should have a dispositive to produce, let's say in this first case, this vibration. So this vibration would be a codimension to the vibration, the foliation defined by pi. Forget G, forget F. Pi defines the foliation of codimension 2 with fibers. And it's a foliation of codimension 2 contained in the leaves of F. And if we are in this situation and do reduction mod P, you recover the fibers of pi as the foliation defined by this guy. So somehow, if you have to look for this map, you know where to look for it. It will come from this foliation that we produce. It will reduce to this foliation that we are looking at in positive characteristic. So
conversely, this foliation like this sub-foliation is still closed. This means that we have a pullback because
it's not completely clear. It's not completely clear, but yeah, I do believe that's true. But if this foliation characteristic P is P closed, I think you need first to prove that upstairs it's unique. There is a unique lift. In principle, the lift is not clear if it's unique or not. And in that case, I think that the known versions, and if you need to have some singularities, because there are versions of there are positive results towards the Ekedal, Scheffer-Baron, Taylor conjecture that could be applied in that case, but you have to have some leave, algebraic leave for this foliation. Yeah, that's the idea. I would love to prove that. So if you want a very concrete conjecture, is that if there is a foliation E or G on V in characteristic 0, codimension 2, tangent to F, that reduces to these guys for almost every P, prime P, then, and it's P closed in these primes, then the foliation should be algebraically integral. We should be in this case. But yeah, we are a little bit far of being able to state results like that. But what we have, we are able to prove baby versions of that statement. For instance, that at the same time are statements about the irreducible components of the space of foliations on Pn. So to have really an example, a Birational example. You just take pi from Pn to P1 times P1, a foliation defined, a morphism defined by linear forms. And you take G foliation on P1 times P1 with canonical bundle so this is everything over C. With canonical bundle A plus B, with A greater than 0, B greater than 0 and A plus B greater than 1. I'm avoiding the case of trivial canonical bundle. Then varying I and J, we obtain an irreducible component Kg. Varying pi and j, we obtain a reducible component of this space here, omega in order 0, Pn. Perhaps I will write on the side. After writing this, I will stop. Reducible component of the following set, omega and F, the foliation. The foliation defined by omega, F defined by omega is equal to pi star of J. So of this guy. So of course, I can just vary the linear forms, vary the one forms here, and I will look at all the foliation that I've described in this way, take the Zariski closure, and it will be a reducible component of this set that we call the space of foliations of Pn of degree A plus 2, A plus B. Okay. And the proof of something like that is essentially this. You start with one example, with this guy very general, with no invariant algebraic curve. We look at this foliation TVF. You have to prove that this guy will vary well in family, that when you move when you form your foliation, this guy will have the same degree. And that happens if G is sufficiently general. There is a study of this divisor that I didn't describe, but for general foliation, this divisor is reduced, and when you move, it moves in a flat family. And with that, you can show that the foliations close to this guy has the subfoliation of the same degree. Here, the degree is very low. It's not 0, but it's 1. And working a bit, you can prove show that any foliation sufficiently close to the initial one has the same description. And so this is, I think, it's just it's a modest result, but somehow this is a subject that I like a lot. Also describing the irreducible components of this set. Is that somehow understand geometrically what Frobenius integrability condition means. And it turns out that computer experiments indicates that all these irreducible components that are getting with these results are generically non-reduced. So it's hard to approach them with the methods that were used before. So yeah, it's just a simple application, but do not seem to be available to the methods that we had before. So perhaps this can be used to other things. Thank you. I'll stop here.
Any questions?
George, do you have an example where PF is not P closed, like it's lifting over?
Yeah, you can. We have. Oh, this guy is not P closed. Yeah, there is one very interesting example. It's essentially the only example that you can do all computations without problem. Is the logarithmic foliations. Because when you have something like this, something which is logarithmic, the Cartier transform of this guy is quite easy to compute. The Cartier of this guy is some lambda I1 over P dFi over Fi. So if you just take this guy not in FP, this will not be, if this guy are sufficiently generic, intersecting transversely and define a simple normal, the polar set is a simple normal, polar divisor, a simple normal crossing divisor, and these guys are not, the quotients are not in FP, so it's not pre-closed. Probably, no, you must, some arithmetic condition will guarantee that it's not pre-closed. So it's, and in this case also it's very interesting because in this situation, the lift is not unique. If you apply the lift and try to understand, imagine that in characteristic 0, you have a bunch of transcendental independent numbers. And when you do try to lift the kernel of this guy, you're going to see that you'll go in every direction. It will be forms, will be defined by forms of the same type inside the guy. So yeah, the lift is not unique and does not, oh, in this case, it's pre-closed, sorry. This example, no, this example is not pre-closed. This guy generically is not pre-closed. Yeah. Yeah, I don't know, I don't have a conjectural description of this guy. So here we already discussed what we should see in characteristic P for every P. I'm not sure what we should see in this situation. But there are, for instance, I think there is one important conjecture in the subject. We have essentially not discussed the foliations that are P-closed, right? And people believe that P-closed foliations, or people conjectured, without believing it, if I understood correctly, that foliations whose reduction mod P is P-closed for almost every P must be algebraically integrable in characteristic 0. So this is a conjecture of Ekedal, Scheffer-Barron, and Taylor, but at least one of the authors do not believe in the conjecture. Does not believe in the conjecture. And
It's also called Grothendieck-Katz conjecture.
No, that's Grothendieck-Katz is more special. Grothendieck-Katz is for connections. Here we are in the nonlinear case. It's not connection, foliations. But you're right. Grothendieck-Katz connection is a special case of Ekedal, Scheffer-Barron, Taylor. And perhaps this author that does not believe in the conjecture is correct, but I still think that this thing should be true in codimension 1. What Grothendieck-Katz for rank 1 connections is known, it's not that hard. It's not trivial, but you can explain in 1 hour to anyone. And I believe that codimension 1 should be doable. And for this codimension 2 tangent to codimension 1 foliations also, and for them should be even easier because you have more structure. But it's just what I believe, it's not a result. As there are results, for instance, in the Ekedal, Scheffer-Barron preprint, they have a result if you have a compact leaf and you know that on the compact leaf, Grothendieck-Katz conjecture is true for the bot connection on the compact leaf, then the Ekedal conjecture is true. Ekedal, Scheffer-Barron conjecture is true in that foliation. So here in codimension 1, bot connection, the Grothendieck-Katz is true for bot connection in codimension 1 because it's the case of rank 1. And it's true also for codimension 2 tangent to codimension 1. So there is some hope that perhaps things, this would be more treatable, but not that I have an idea how to do it. But.
Any more questions or remarks? If not, yes. Thanks, Jorge.
We move to the next room. Now we take out a bit of food, a bit of drink. Who wants to stay longer? Chat.